Okay, welcome back to our last main unit for this semester, and that is Chapter 5, which deals with harmonic motion. We're going to throw in Section 6.1 because it is important that you see series solutions, but the big emphasis in this last section will be the harmonic motion, dealing with how do we get things to oscillate, especially in the case where the oscillate gets out of hand and you get resonance. So we're going to take a look in 5.1 at just what are the forces involved here, what are the issues involved here. You'll notice Section 5.1 has no homework, so of course your homework in this section is to give me one of your stories, since I'll be giving one at the end of this talk. So our setup is dealing with a spring, although the same principles can be applied to any type of oscillation, motion being water waves or sound waves or even light. So we have a spring hanging from the ceiling here. It's just going to be sort of sitting there, and then we put a mass on it. And it's going to stretch that spring a certain distance L. Once it comes in equilibrium, then we're going to call that position for the mass x equals 0. Sort of weird talking about x being a vertical thing, but these are what physicists do. So x is a displacement. It's going to be a vertical displacement. Positive is going to be down, again, following typical physics notation here. And that makes sense if you think about it in terms of the length of the spring. As we go positive, we're stretching the spring more, compressing the spring is negative. Okay. Well, we can look at Hooke's law. It says the change in the force exerted by the spring is some constant times the magnitude of the change in where x is. Okay, now x can be positive or negative. The main thing here, though, is notice once we've got an imbalance, we can really not have to worry about what L was, except for a couple specific cases which we'll deal with. We are going to assume that when we're moving this thing up and down, we don't get this thing oscillating so much that it goes past where the spring would be with no mass, in which case the spring would overcompress, it would contact itself, and it would obviously bounce, and that would violate all our rules. We're also assuming that we don't pull it down so far that the metal overstretches and can't retain its shape. So we're staying within the reasonable realm there. And we'll notice in that case, K times L, okay, so how much the change in the force was by moving this mass down was equal to the weight of the mass, mg. Okay, so the mass started up here. Now, I do the mass pretty big here. We're sort of assuming it's a point mass kind of thing, so we're not going to worry too much about that. But obviously, it's to the center of mass. Okay, so if we know how much length the spring is added by a certain mass, that tells us what the K is, so we can experimentally do that. Okay, so x of t is our location at time t, and we want to look at the basic Newton's equation, force is mass times acceleration. So we have mass times x double prime of t. The first force we have on it is the spring force. And the spring force, we go minus kt. Notice from up here our k is defined to be a positive k, because those are absolute values there. And so we put an opposite of kx because the force of the spring is always going to be the opposite of where the position is. So if it's up here, the position is negative, and so the force is going to be downward. If we go down here where the position is positive, the force is going to be pushing you upward, which is in the negative direction. So that's why the negative sign is there. Notice we're only thinking about x because we've balanced this thing out. So the weight of this mass is not changing as it's oscillating up and down. Obviously, we're assuming we're not going distances where the distance from the center of the Earth matters. However, this is usually where we stop in sort of a high school application. We want to add in the things that are out there in real life. And the one thing we tend to ignore in a lot of idealized situations is friction. So we're going to add in a couple more forces. We're going to put F2 is our friction. And F3 is going to be some external motor. Okay, so those are things that are usually ignored, obviously, in your traditional physics, first semester physics courses, because obviously you need differential equations to address them, and that's not usually a requirement in those courses. Okay, obviously nothing is frictionless, so F2 is going to be friction. If you want to be technical here, this is dynamic friction, because the thing is in motion. So it's going to be a combination of a certain amount of energy absorbed by the spring, stretching and compressing, converted often to heat. And then, of course, the actual air resistance of this mass or whatever as it's moving up and down, especially if it was in something thicker than air, maybe it was underwater or something. And of course, external would be some type of motor you're hooking up to this thing. So, for instance, if you have a battery-driven clock, the mechanism is driven by a battery, which is causing the gears to move in some manner. Now, it depends upon how it's geared. Nowadays, of course, everything's digital, so probably wouldn't be using an oscillator. Okay, so let's think about what those two terms are. Friction is always moves against the direction of motion. Okay. And so that's going to be some constant. And we have to think, well, friction depends not on where you are, but on how fast you're moving. So if you're just standing still, there's no friction. However, friction is generally, unless you're in something really thick and viscous like molasses or whatever, it's going to be proportional to your velocity, which is so minus a x prime. Okay. So there's our friction term. And of course, our external motor, we're generally going to be dealing with some type of oscillating motor. So we're going to be particularly interested in where this is some type of a trig function. But for right now, our external force is just going to be some capital F of t. And so we get this equation. Our forces, F1 plus F2 plus F3, is m times the acceleration x double prime. F1 is minus kx. F2 is minus ax prime. And F3 is, we're just some function, capital F of t. So we often move the other things over to the other side, and we have capital F of t is mx double prime plus ax prime plus kx. Okay, so that's our general spring equation. Now we're going to handle this in several stages. The general case is fairly complex, but we have a whole chapter to go through it. First of all, we have to identify what we're going to use the terms for this. First of all, if we're looking at the idealized frictionless cases, so if A is 0, the motion is called undamped. Got to make sure you put that P in there. Okay, so undamped motion means that we're not including friction. Obviously, this is an idealized situation since in reality, nothing is ever frictionless. But if you had something, say, that was being oscillated by magnets or in a vacuum, you might get close to this situation. And of course, if A is greater than 0, the motion is damped. And of course, that's normally a case that's sort of ignored in most first semester physics courses because, again, you need differential equations to solve it. If f of t is the zero function, we have free motion. Okay, so, and if f of t is non-zero, it's force motion. Okay, so that's the terminology we're going to use. So we're going to start with sort of the simplest ideal case, which never actually happens, and that is the case of free, so no external force, undamped, no friction model. So in that case, we simply have 0 equals mx double prime plus kx. That would be free, undamped. And then we're going to, after that, proceed. So that's going to be section 5.2. After that, we'll add in the friction. So that would be free but damped motion. And then we're going to go to forced motion. So forced damped motion. You could have theoretically forced undamped motion. And that's often sort of this overly simplistic method people use to explain things getting out of control and getting some type of harmonic oscillation going on there that's going to get you in trouble. But in reality, everything has friction, so we do have to deal with how do we get resonance when we include the friction term. Okay, so that's the plan of action going forward. And so that's the end of section 5.1. Since there's no homework on this one, I'll tell you a story before I let you go on this one. So these 3 strings walk into a bar, and they've had a hard day. Hopefully I haven't told you this one. And go up and say, "Bartender, give us beer." The bartender says, "We don't serve strings here," and throws them out on the curb. Well, they're not happy about this. So one says, "Well, let me try this." He puts on some shades and a trench coat, walks in, tries to act cool, and says, "Bartender, give me a beer." Bartender looks him up and down, says, "Aren't you one of those strings that was here earlier? I told you to get out of here," and has the bouncer throw him out. Well, now they're really upset because there's clearly discrimination against textile materials. So they got to figure out some way of doing it, and they're thinking. Finally, one of them says, I got it, but you're going to have to trust me on this one. You're going to have to beat me up, put a big old square knot in me." And his friends look at him like he's nuts. But he says, no, trust me on this one. So they say, okay. They rough him up, and he's staggering around. They tie a big old square knot in him, and he staggers into the bar, barely able to walk, and goes up to the bartender and says, "Bartender, I really need a beer." And bartender gives him a second look and says, "Hey, aren't you one of those strings that was in here earlier?" And he looks up and says, "Nope, I'm afraid not." Okay, have a good one, and look for section 5.2 to come out soon.